Awesome.
Sorry. Oh, I'm sorry. No, here's
When is the Johnny ASCII update coming?
Oh, you did. Here's the question.
Actually, let's do this. Okay, look up, please. Hey, somebody just start us off. Just remember from the notes, when you are presented with a limit problem, somebody by raise a hand, just remind us what's the first thing we should be thinking of doing. Factor and divide if we can. Remember, on the written portion of the AP test, you got to make sure you write it correctly. So I want to tell the grader I understand that this next line is equal to the previous. So I write limit again. Last time when we factored, it was a binomial type factoring. You don't really have to remember those terms, to be honest, but this factoring is easier because we're just going to remove a common factor. The common factor is x. Somebody else get in on the participation, just what's left, like what do I write inside the parentheses once I do that? Maggie?
5 minus x minus 4x squared.
Nicely done.
Mr. Smith, do you have Justin Hartshorn?
No, he's in my class, but he's not here yet.
Okay, perfect. If he does show up in a minute, he's being checked out. Thank
Okay.
you.
Somebody back to the bottom for me. Elliot.
3 plus x plus 2 cubed.
Nicely done.
Or 2x cubed.
Good enough. You're good. We have a question. Okay, so the x and the x can divide to make 1 as long as x does not equal 0. But because we are finding a limit, we're not really thinking about x equaling 0. We're thinking about x being extremely, really close to 0. So the division is legal. So now we have this, all right, equal again. Okay. The second step I gave you was to check and see if x is approaching infinity. It's not in this case. We'll do an example of that in a second. Third thing I said was check the right and left limits. Okay, at this point, if you want, you can save a little bit of writing. Last time I wrote out, check the left limit, check the right, so you clearly understood what I was trying to say. But here, if you want, we can just kind of mentally think about it. But it is critical that you remember you are checking the left and the right. One of the biggest mistakes is people fall into a habit of thinking they're plugging in 0. In fact, in A1 and A2 today, as we practiced on the homework a little bit, people were already doing that. We're not considering x equals 0 at all. Numbers that are close to 0. If you plug in x equals 0, you have to plug it in up here, and you definitely get 0 divided by 0, which is undefined. The value of this limit is not undefined. It's what's happening when x is close to 0. And again, remember in my class, you don't have to have a question. Just anything that just kind of comes to mind, just raise your hand and we'll just talk about it. So, anybody? Please.
Do you not need to factor that more?
Outstanding question, actually. So when you look at this, you kind of say, well, wait a minute, that's a quadratic. Maybe I can factor it. That's where, honestly, step 1 and step 2 in finding a limit kind of overlap. I've learned from experience that I definitely want to look to see if I can factor first. But I've also learned from taking a lot of AP tests that they don't typically, so this is kind of just a test tip, They don't typically give difficult factoring. So I kind of glance at it, and if it's easy, I like to do the factoring. At a glance, that doesn't look easy, so I just kind of, I'm not going to worry about that yet. Let's see if the next step will kind of help. But it's kind of tricky. It's really based on experience. Just kind of doing problems, just start to get a feel for when you can factor, when you can't. Outstanding comment. Anybody else? So I want to think about plugging in a number that is almost 0. So I'd like everyone to do this mentally. So let's kind of think of a number that's slightly bigger than 0. So that's like 0.000, forever 1. Let's see, if I put that in place of this x, and I put it in place of this x, these three terms will add together. And I'm thinking that, well, I don't know, see if you can think how I'm thinking. So just raise your hand if you think what the numerator is going to be. If you plug in a really small value for x, you add these three things together, you're not expected to know exactly what the numerator will be. You're simply expected to know what the numerator is going to be very close to. So hands up if you know. Just waiting for the whole room here. Give me a chance to think about it for a second. Let's try Abby.
Maybe like close to 5.
It's close to 5. That's very good. Because we're adding something to the 5. We are. A negative, tiny value. So the 5 does change in a very minuscule way, but not enough that we really concern ourselves when we're solving for a limit. Over here, when we square that tiny value, multiply it by 4, it's maybe not as tiny, but compared to the 5, it's still kind of insignificant in terms of a limit question. If we were trying to find the precise value of the function, we would have to get out a calculator and do it. But in terms of a limit, we're just looking to see what happens close. So 5 is sufficient. It's perfect. Question. One thing. Notice how I'm comparing terms that add to each other. I'll keep reminding you, but don't ever try to compare terms that multiply by each other. That's not really easy to do mentally. Adding is simple. 5 plus extremely tiny is basically 5. One year I was teaching this, and somebody was like, this is like the coolest math ever. It's like, 5 plus tinier, oh, that's 5. Interesting rules. Raise your hand if you can tell me what you think the denominator will be when x is really close to 0. So all we know, what do you think the denominator will be when x is really close to 0? So Brooke. 3. Question. Perfect. Hey, answer this. I was kind of thinking of a number that was more than 0, just like barely more than 0, because I do have to check left and right. That's critical. If I think of a number that's barely less than 0, does it really change, or is the result basically the same? About the same. So I know the answer to the limit now is just 5/3. And that's sufficient. You don't have to do anything else. Please.
So do not say like equals about 5/3, it's just equals 5/3.
Oh, outstanding. If we were really looking, good job, Matthew. If we were really looking for the actual y coordinate, the answer wouldn't be 5/3. But in the limiting sense, we're just trying to find out what we're getting close to. 5/3 is great. Please, Peter.
I don't understand how the tops and the bottoms, like numerator and denominator,
So are you okay that once we get to this point, the remaining step is to literally choose an x value that's barely more than 0 and another x value that's barely less?
Yeah.
Good. So let's think of the one that's just barely more for a second. Are you comfortable that if you take 5 and add to it a negative tiny value, you'll basically end up with 5?
Yeah.
Pretty darn close. Is that fair?
Yeah.
Now when I say tiny, you have to really stretch and think of a number like this. 0.0000000000000000000, and just keep listening to me for about 18 years. I'm serious. Like the idea of infinitesimally small is really difficult to think of. So 5 minus that, it's pretty much 5. I mean, it's going to be 4.999999999999999 forever. So that doesn't really affect the 5 hardly at all. This one, same thing really. So when I add that term, the numerator is not becoming 5, but it's getting really, 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 really close to 5. And the denominator does something similar. I don't know if that helped or not.
Well, I just, well, because like once you put the extremely small, the 0, 0, 1, where the 4x squared is, so then wouldn't you be minus 5 minus 4x?
The thing is, though, that this term, once you plug that tiny value in, square it, multiply it by 4, it's still a number like this. You ready? 0.00000000000 for 20 years, and then it's like 3792. But 5 minus that's 4.999999999999999999999.127.
So that even if you multiply 4 by
The 4 makes it a little bit bigger, but think of this. If you've got, you know, 0.00 forever and you multiply it by 4, all you have is 0.000 forever 4. Like, it doesn't make a difference. It's kind of weird, but think of this one. Gotta erase this, hold on. This 4 right here, you could really have 12 trillion in place of the 4. It still wouldn't make a difference. Because you have to think in a little bit differently. You have to think of the fact that what you're plugging in for x is so small, it doesn't matter if you multiply that value by, I can't even think of the number, you know, like 5 quintillion. It still doesn't matter because the x value itself is infinitesimally small. Like, it is so small, it's never going to make a difference. Like, it makes some minuscule difference, but not enough to really say that we're getting close to anything other than 5. Does that help a little bit?
Yeah.
The questioning is really good. I hope that's helping a little. So. Anybody else? Awesome. Next one. Go to 17. Okay, so this is related to what I said to Carrie. I've taught you that step 1 is always factor and divide if you can. The reason I told you that was step 1 is because so many students have forgotten the step in past years that my theory is that if I keep telling you it's step 1, you won't forget. But really, step 2 and step 1 are kind of evaluated equally. So when I saw that this was x approaching infinity, I didn't worry quite so much about factoring. But I go back to the same technique I just showed you where I'm going to compare terms that add. And it's the same idea that I was talking to Haley about, that now we're choosing an x value that is, it's just really hard to talk about because it's so big. In fact, you could play a really dumb game. You could say, let's see who can name the largest number. So here's a weird question. I don't do this all the time, but I'm going to give a full extra credit ticket if you can answer this. So at the end of the period, I'll give you one free, just full extra credit ticket if you can answer this question. And it's not meant to be a trick. I just want you to think about it for a second. We play this silly game where I say, we want to find the person who can name the largest number. And they don't have to have a name for it. You just have to say it. Like, well, I say the number is 1000. And then we say, okay, can somebody get a larger number than that? Somebody else raises their hand and they say, well, I'd say 1 with 6 zeros. And say, can somebody else pick a larger number? And they go, okay, I say 7 with 8 zeros. Here's my dumb question for extra credit. Pretty sure if you can tell me who's going to win the game. It's kind of a trick question, but it's not. I'm not trying to trick you. I just want you to think about it. Who's going to win this game? The answer is a bit of it's a trick question. It's like, who's going to win this game when I say we want to find the person who can like describe the largest possible value? Because that's what we mean when we say x approaches infinity. Talk to each other. I want everyone to get this ticket. Like, what's the large? Like, explain my trick.
What did you get?
Raise your hand if you know. Who's going to win the game? Who's going to win? Raise your hand if you know. Raise your you don't raise your hand, you don't get the extra credit ticket. I want to see if everybody knows. Who's going to win the game? Let's try Brennan.
Like the largest infinity, I guess?
You're on the right track. Who's going to win the game? Who's going to win the game? Let's go Ayla.
I feel like no one because numbers are close.
That's the idea of infinity. There's no, you just, like, as soon as you name a number, like Carrie said it really well, as soon as you say, oh, I think the biggest number is such and such, I go, well, just add 1 to that. That's bigger. So when you think of infinity, it's like it just goes forever. There's no limit. It stuff never ends. So when we make a comparison here, so that was just a free ticket for everybody. Oh well. What question did it work out quite how I wanted? How many knew how many knew the answer? Show me that. Good one. Okay, we just compare again. Okay, I'm going to plug in this infinite value for x. It doesn't really matter that I'm multiplying by 7. Who cares? But when I add it to negative 12, just say yes or no, please. Does the negative 12 make much difference? Yeah, very, very, like, unbelievably small difference. So I kind of ignore negative 12. Now compare these two. The leading negative is important because that makes this value a negative value. But when you square a number like we're describing, it becomes so much bigger than the one that was not squared that it's kind of like doing this. It's kind of like having a number and then when you square the number, you get something like this. This gets tedious very quickly. The squared value is so much bigger than the unsquared value that when you add them together, this completely dominates. It's kind of like money. If you are, you know, someone like Bill Gates, and you have billions of dollars, well, thousands don't really make a whole lot of difference. They just don't. So when we answer this question, we simply compare the terms that are adding, and we say, really? If you let this grow forever, when this gets big enough, you won't notice that these two terms are being added to that term. It will dominate. It's the highest power term. So I just say equals limit. I must include the negative. That's important. X approaching infinity. And all divided by the bottom, same type of comparison. I want to talk about how I got there. It's basically like we could spend a day playing on the calculator, and I could have you type in different numbers and have you just experiment. And you'd come to the conclusion that, oh yeah, you're right. This term always is so much bigger than that one, it doesn't really make any difference. And that's all we're doing. So just comparing them. The key thing is that they're both power functions. This is x to the first, this is x squared. And with power functions, the power function that has the highest exponent is going to dominate. Okay. Some of the homework questions deal with exponential functions, like e to the 2x or something. Exponential functions grow much faster than power functions. So if you had an exponential added to a power function, it wouldn't matter if this exponent were extremely large, because x gets bigger and bigger forever. This will eventually be much larger than this, and this will dominate. So part of it, Avery, really is just kind of memorizing which term is dominant. Yeah. Other questions? Awesome. So, let's see here. Oh, this now reduces, though. If you divide negative x squared by x squared, you just get negative 1, which is telling us that no matter how large of a value we plug in, the top's always exactly the same as the bottom, except that there's a sign difference. So this limit is just negative 1. Question. Please, Maggie.
So if you put in a negative, then it would be minus x squared over x squared?
Outstanding question. So here's what you're thinking. You're making a tiny error. No big deal. I'll just show you how to correct it. The Negative is outside. Remember how I talked about whenever you replace a variable, make sure you put parentheses. So if you were to put a negative value, now we won't because we're choosing x to get bigger, bigger, bigger. But even if we were to put a negative number in that was large, like very negative, that negative number gets squared first, making it positive, and then it becomes negative. Other questions? Awesome. Okay, so erase this for a second. Let me show you something about the homework tonight. So, you probably noticed, but every time you do a homework problem, just turn to the back and confirm that your reasoning is correct by checking the answer. Every homework packet I give you, I will give you every answer. If you really think about it, there's no reason not to. You can literally, I mean, if you want to cheat, who cares? You can literally get on Wolfram Alpha and like just type in, please solve this limit problem. So the answers are to help you quickly get feedback that, hey, I'm on the right track. Okay, warning, don't ever work an answer backwards. Don't ever you look at the answer and then like dream up some sort of mathematical process that somehow results in the answer. That's a waste of time. You might as well just burn this. It won't help you a bit. Okay? The proper way to do homework in calculus is, check your notes, watch the video if you need to, get my help if you need to, logically think through what you feel like the result should be, check your result. If it matches, that's a confirmation that your logic is sound. If it doesn't match up, then check your logic again. It's still not matching, just go on to the next problem. Here. So I'll get you guys to help me. So x is approaching infinity. I could factor if I want to, I can. But they're both, the terms are just adding. So just doing my little comparison goes pretty fast. So I think I'll skip the factoring on this one. So just everyone in the room, look at the two terms in the numerator. Just raise your hand if you feel comfortable as to which of those two terms will dominate. Just want to check the whole room. Which of the two is going to be the dominant term? Meaning we only need to worry about the dominant term. Lauren?
Yes.
So Lauren says 2x cubed. So I rewrite this as the limit as x approaches infinity of 2x cubed. How many would agree with Lauren? Show me that. You would have a question. Now look at the bottom. Do the same thing. Hands up, please. Again, remember the sign that's associated with the term is important. So go to Brennan.
Negative 4x squared.
Important that you say negative 4x squared. I have a question on that. This reduces again with division. So we'll do that. So somebody tell me what would be the new expression I could write if I do some dividing here. Let's go, Maria.
Here. So it's x cubed over negative 2x squared.
So she divided the 2 and the negative 4.
Yeah.
Oops, I did something wrong. Hold on a second. No, you're doing just fine.
Okay.
We can divide again. That's what you're thinking. So somebody else get on the participation here and the next division. Let's go over this. Well done. Anyone need further explanation to there? Does that make sense to you so far? Oh, please.
Sorry, so we can simplify it. This is kind of a concept that was kind of hard to have here. So like when you add something, then you can't simplify the denominator, so it's multiplying or exponent.
The key thing is that you can only do this division. Like what we're doing is we're saying 2 divided by 4. We're saying, you get that part, we're saying 2 divided by x squared. The division is only allowed if both numerator and denominator are in factor form. So you look at the numerator and you say, oh, this is factored form because I've got one factor multiplied by another. That's when you can divide it. So keep asking that. That's actually a commonly difficult thing to grasp. So just every time that comes up, just keep asking. Anybody else? Okay, it's time for a thought experiment again. Okay, x is going to grow forever. Okay, first of all, don't worry about, this is really important advice. Don't worry about the positive and negative. Leave that for last. You've got a number that grows forever divided by 2. Well, will that resulting value, just think of it in terms of a few choices. Will that resulting value just continue to get bigger and bigger and bigger as x gets bigger and bigger and bigger? Will that resulting value kind of stabilize to, say, 5 or something? Or will the resulting value get closer and closer and closer and closer to 0? Those are the 3 choices. That's what always happens as x approaches infinity. So hands up if you know. Show me. So as x gets bigger and bigger and bigger, you just keep plugging in values for x. Am I going to end up with, just remember, when we're finding a limit, we've got a formula for a function. And all we're doing is saying, if the x-coordinate is this, what's the y-coordinate going to be? That's all we're doing. So we kind of reduced the formula to something easier to think about, but it's the same process. You plug in this number, it's bigger and bigger and bigger. Will this resulting computation continue to get bigger and bigger and bigger? Ignore the negative for a minute. Get closer and closer to 0, or will it get closer to like a number, like 7 or 5 or something? Hands up. Come on, show me. You know. What's it going to do? What's it going to do? Let's go math. Okay, closer to infinity. Just keeps getting bigger. Because all you're doing is dividing it by 2. So it's the dumb game again. It's like you put in a number, you divide it by 2. Like, hey, it's shrunk by a half. Well, who cares? Put in a bigger number again. It just keeps growing. Okay. Give me 0 to 5 if that makes sense. I don't know why I refuse. I'm kind of a rebel. Like the standard teacher thing is to say fist to 5, and that just bugs me. So I had to make it my own. I don't know. Okay, good work. Cool. Questions? Pretty good? Awesome. Then you worry about the negative. Okay, look at my hands. Look. When you think of a number line, let's draw it here. When you think of a number line, okay, technically, the numbers are from least to greatest. Is that okay? Nod? Yeah? Okay. However, there's another way to think of it, which is equally valid depending on the situation. It's equally valid to think of this as being a very large value, this also being a large value. Large positive, large negative. Does that feel okay? So it kind of depends on the problem which way I think about it. In this case, what I think is I'm plugging in a very large value, dividing by 2, so I know it's growing to infinity. However, positive divided by negative is negative, so it grows to negative infinity. That's how I would think through 18. Questions? Perfect. Very good, very good. That's why I say, Avery, I don't worry about the sign until I've done thinking about it. The sign is the last thing I worry about. The result's either going to be positive or negative infinity, some number, positive or negative, like we did here, or 0. There aren't any other possibilities. So. Please, right.
When you're like writing that, like doing your work, would you want to put like the limit if x to negative or x to infinity every time, or would it matter like if you went like 2x cubed over negative 4x squared equals then x cubed over negative 2x squared?
Oh, gotcha, gotcha. Everybody hear this? Everybody, look at me, look at me. No, really good question. And I'm not sure I heard it perfectly, so just interrupt if I get it wrong. When you're solving a limit problem on the written portion of the test, it's crucial that you use the equal sign properly. This formula, watch me, this formula isn't equal to this formula. It isn't. What's equal is this limit is equal to this limit. So you've got to have the word limit. Otherwise it doesn't make sense. Is that kind of what you're asking?
Yeah.
Yeah, it's perfect. And then another thing to help with, 1 second, Sam, sorry. Okay, it's early in the year, so I tend to show a lot of steps because I don't want anyone to get lost. But I also want to give you good guidance as to what's required on the AP test and what's kind of just good practice to avoid mistakes. So I'll be honest with you. After you get through with this homework, most of you won't need to write anything to answer this question. You literally will just think about it and write down negative infinity. And even if that were an AP test question, that really would be sufficient. They wouldn't require you to write all of this. This was just to help.
So if, let's say, it's a different problem and it's -2/x, would that still be negative infinity?
Oh, outstanding. Let's write it down. One second. Sam, I need to get back to you.
Oh yeah, so when you're talking about like correct mathematical
Notation.
notation, that's what you're talking about, is right, like limit.
Yeah. The word I use is you have to properly maintain the equality from line to line. You can't declare two things to be equal if they really aren't. That's an error. So, does that make sense?
Yeah.
Good one. So Olivia's question is, what if this happens? 1 second, I gotta find a place to write this down. Just let me erase this number line. What if the result of your kind of simplifying it, you end up with something like the limit as x approaches infinity, and what did you say again?
Oh, like -2/x.
Oh, very good, perfect. Everyone in the room can get this one. Now remember, as I said to Maria a second ago, or it was Avery, there's only 3 possibilities. And again, don't worry about the positives and negatives. That's the easy part. As x approaches infinity, the limit's either going to approach infinity, some value, or 0. Okay, there could be a positive or negative, but anyway. This one's a negative divided by a positive, so the result could be negative infinity, 0, or some negative number. Now, those are the only 3 choices. So think about this. You have a constant, 2. You're dividing by something large, so it's like this. You have like 2/10. And then you make x get bigger. So you have 2/100. X gets bigger. 2/1,000,000. Just say it as a class. Are these successive fractions getting bigger or smaller? Smaller. So are we approaching infinity or 0? 0. Yeah, this would be 0. Does that help? Anybody else? Awesome. Yeah, most of the time, the limit problems are a really good place on the AP test to pick up some good, easy points. Like but it's all about understanding it. You can't mimic the teacher. You've got to make sense of the idea so you can apply it to a brand new problem. Good work. Any other questions here? So grab your white sheet that passed out last time. There you go. I was just okay. We're going to talk about the graphical side, so look at this side. Okay, look here. All right, let me get it up on the board so I can talk about it more easily. Put that there for a second. 1 second. I got this, another teacher was kind enough to let me use their worksheet. They designed it a long time ago when computers weren't quite as good at graphing. So you have to make one little mental adjustment to this graph. Think of this dot as being more like about this size. Okay? It's way too big. It just kind of obscures the fact that it's really supposed to be infinitesimally small. But you can't draw something infinitesimally small and still see it. So this is the best we can do as feeble human beings. Good? Same thing with the open circle. It really should look like this. Like this. That's even too, that's a little tough. It really should be like as small as you can draw it and still tell that it's an open circle. Okay, so don't think of it as being large. Very good? Okay. All right. This this worksheet is like the best example I have so far of what it really means to understand something versus just memorizing something. I'm going to teach you how to properly read a graph, which may sound silly because you're like, well, I learned how to graph in like 6th or 7th grade. but I really believe that you were never taught really what you're doing. And if you learn it properly and it makes perfect sense to you, you'll never forget it. It's really easy. And you will never miss a graphical limit problem ever on the AP test or on my test. It's really that straightforward, as long as you make sense of it. If you just try to copy what I'm doing, you'll miss them repeatedly. So here we go. Okay, remember, we talked about how a function is always a list of x, y pairs. The graph's just a picture of that list. That means when you look at a graph, you're seeing a whole bunch of dots. And each dot has an x and a y value. We read the graph from left to right. And as I read the graph, I notice something. Let's actually, no, this is good. So I go left to right, and I notice, hey, no matter how hard I look, I don't see any dots over here. Which means if I were making a list, a table, the table would have no values for x's that are like over here, like -3, there's just nothing. There's nothing defined. In fact, the very first dot is right there. And that location is -2, and the y coordinate is 0. Label that. Okay. Because this is a function, you can't have two dots at the same x coordinate. So the next dot has got to be to the right of the current dot. Now, one thing that messes with people is you're used to graphing where the dots always connect. They're always adjacent to each other. They don't have to be. And in this class, they often are not. So when I go looking for the next dot, I don't look for one that's right next to this dot. I just go looking for the next dot, wherever it happens to be. And I find it, it's right here. Like to the right of this dot, the very next dot is right there. Question. Now the open circle, I ignored that, because that open circle has exactly the same meaning as all of this open space. Like, it may sound silly, but I could draw a little circle here. There's an open circle. Here's another one. Here's another one. Here's another one. They all mean the same thing. They don't mean anything. There's nothing there. The dots are what represent the function. Questions? Cool. Let's get rid of those just because they're kind of annoying to look at. Okay, the reason they put an open circle there is not because it represents something. Like, people want to say, wasn't that a hole in the function? Yeah, I suppose, but a hole means nothing's there. So it doesn't mean anything. In fact, here's what I do. It's my little invention. I label that location like this. I use dashed lines to indicate that it's like a ghost point. There's nothing there. Yeah, it has an x-coordinate. The x-coordinate is 2. And the y-coordinate is 3. But there's nothing there. The only reason they drew the circle is so I could find the location of the purple point. The reason for the open circle is so I can find the location of the purple point. I can do that one. In fact, let's check the whole room again. So if this dot right here is at -2, oh, sorry, that's negative up here, my bad. If that dot is at -2, 0, the very next dot has an x-coordinate. Raise your hand if you know the x-coordinate of the very next dot in sequence. Oh, no, come on. What's the x-coordinate of the very next dot? Let's go, Mason.
Oh, the very next dot after like that.
After the -2.
That's like -1.99.
Very good, very good. No, it's perfect. What's the little shorthand notation we use that means the exact same thing, Andrew, as?
Would you put limit x and then an arrow to -2?
Close. Got the right idea. I'm not doing a limit problem. You have to try on the right track. I'm just trying to figure out what the x-coordinate is. No worries, dude. You're right on the right track. Brenda.
-2 plus?
-2 plus. If this is at -2, the next dot has to be at an x-coordinate of -2 plus. Questions? Or do you want me to say it differently? Okay. Because I know the location of the ghost point, I also know the y coordinate of this point. Because this ghost is at a y coordinate of 3, so what would you kind of think the y coordinate of the purple dot would have to be?
3 minus.
3 minus. It's just barely below where the ghost is, that open circle. Question. Perfect. This is how you read a graph. If you can read the graph and it makes sense to you, you really will never have a problem with the limit question in this graphical. They're just that easy. They can't trick you. There's no way to trick you. We could spend a lot of time writing down what all these are, but it gets a bit tedious, so we just kind of breeze past that. Here's another ghost point. The ghost is at, you'll never read the word ghost point in a map book, but it does help me understand what we're talking about. That's at 0, 0. So that missing point. So that tells me I can locate this dot precisely now. The green one. So let's check the whole room. So raise your hand if you can tell me the x-coordinate of that green dot. What would the x-coordinate of the green dot have to be? All in one. What would be the x-coordinate of the green dot? So Erica?
0, 1, 0, 1.
So Erica says the x-coordinate is 0 minus. The y-coordinate, she says, is 0 plus. Raise your hand if you agree with Erica. Perfect. Question. This gets a little bit tricky sometimes. If this x-coordinate is 0 minus, the very next x-coordinate has to be 0. Are we okay with that? Okay. I'm looking for the point that's located at 0. My eye doesn't even see this because there's nothing there. It's no different than I don't look here. There's nothing there either. I don't look here. There's nothing there either. I look for where there is a dot. Just say it out loud. Where's the y-coordinate of that dot? 3. The y-coordinate's at 3. So the next point is up there. So it's right here. Its x-coordinate is 0. Its y-coordinate is 3. So the graph really goes dot here. We jump clear up to there. And have a bunch of adjacent dots. We jump clear up to there again. Questions? You want me to do it differently? Superb. Okay, now that's 0, so the next one's got to be at 0 plus. So I look up and down until I find the dot that's located at 0 plus, and it's right here. It's getting a little crowded, so we'll just kind of like so. That dot's at 0 plus, and the y-coordinate appears to be 0 plus as well. Questions? Okay, now we can use that information to answer limit questions. So we can look here, and it says, here's the function f. Figure out the limit as x approaches -2 from the positive side. So it's a little bit of a new thing as well. They're not asking for the overall limit, they only want the right-hand limit. Remember, finding a limit is nearly the same thing as saying, here's a function, here's the x-coordinate, please tell me the y-coordinate. Except that it's not really the y-coordinate, it's like what the y-coordinate is getting super close to. So, I go over here and I gotta go to an x-coordinate that's -2 plus. Well, here's the x-coordinate that's exactly -2. For this function, when the x-coordinate is -2 plus, I'm right here at the purple dot. That y-coordinate is extremely close to 3, therefore this limit is 3. Questions? Oh, please. Oh, yeah, very good, Eliza. All of this was me kind of helping you understand how to read the graph. On the AP test, I've never seen them require anything but the answer. Yeah, they just expect you to look at the graph and come up with the result. What they really do to try and fool you is they usually make them multiple choice. And so, yeah, they pick all the answers. They're the mistakes. So if you're not confident in your understanding of how to read the graph, you sit there and second guess yourself. You're like, well, I thought the answer was 3, but wait a minute. You know, you see other answers and then they start to play tricks on you. But, please, Carrie.
Do you have to have the 0 minus?
On,
Like 3 minus?
here?
For the answer, yeah.
Oh, outstanding. No, when you're doing a limit, don't ever put approximate here, and don't ever put a plus or minus. Because limit technically means what y value are we getting really, really close to. And even though the y value is 3 minus, we're getting really close to 3. Great question. Good job. So go to the next one. This is as x gets close to 0 from the negative side. So look at the board. Raise your hand, please, if you can tell me. I got a lot of dots up here. You've got this one here that we'll call red, purple, green, orange. We'll make this one blue. To answer this question, just raise your hand and tell me which colored dot should your eye be looking at. To answer number 2, which colored dot should your eye be looking at? Let's go, Ellie. So Ellie votes green. How many people are willing to vote with Ellie? Show me your hands. Perfect. Perfect. We're looking at the x-coordinate to be a little less than 0. Okay, the y-coordinate is getting really close to 0. Questions? Perfect. Look at 3. Again, hands up. Which colored dot should you be looking at to answer number 3? Which colored dot to answer number 3? So Spencer. Orange. Spencer says orange. I'm going to agree with Spencer. Solid. All right. So that's getting close to a y value of 0 as well. Oops. Well, blue's fine. Okay. Bit of a trick question. Look up. I'm warning you because I told you, I think I told you on the first day, I don't like to fool people. But trick questions are useful in testing your understanding. So I feel guilty as soon as I ask you a trick question, so I have to warn you. This is a trick question. Okay. Ready? Which colored dot should you be looking at to answer number 4? Hands up, you know. Which colored dot should you look at to answer number 4? Let's go, Jared. Blue. So Jared says the blue. Raise your hand if you agree with Jared. Okay, so this is not meant to be a criticism, but the AP test just succeeded in fooling you. Okay, that's what they want you to do. They really do. No big deal. It's just that's why we talk about it. Does that make sense? Okay. When you're, remember the rules. This is what I call the overall limit. In fact, it's really good that you did that. It's perfect. Like half the room fell into the trap. This is the overall limit. When we're finding an overall limit, remember your nodes. What do we always have to check to find the overall limit? Say it, Ellie. Say it. The 2 points on either side. We have to check the left and the right. So to answer this, that's why I said it was a trick question. What color dot should you be looking at? Max? I mean an orange. You don't look at blue at all. Look at me when I say that. You don't look at blue at all. Say it out loud, please. What's the x-coordinate of the blue dot?
3.
The x-coordinate, sorry, x. 0. No worries, no worries. The x-coordinate of the blue dot is 0, right? Okay. We're not paying attention to 0. We're finding a limit. Limit means find when the x-coordinate is almost 0, not 0 itself. So to answer this question, you do not look at the blue dot at all. You are looking at the location of the green and the orange, and you're comparing them. And give me 0 to 5 how that feels. And if you're kind of 3 or less, if you can come up with something to talk, you don't have to have a question, but you can talk to me, it really helps. You want to talk about what's bugging them. You need to pick somebody out. Anybody have an idea of what's kind of feeling just a little unsettled? Let me say it again. Oh, please, Grace.
What would define blue dot?
Outstanding. Outstanding. None. Because it's, yeah, great. That's an actual point on the function. What they'll ask you to identify that isn't a limit at all. They'll say this. In fact, it's down here at the bottom. Next to dump f of 0. Because f of 0 means I want to know the y-coordinate for the function f when the x-coordinate is exactly 0. Does that make sense, Gracie? Good work. Avery, please.
But then, like on number 8, f is 2, so then it's 1. That's like, that's gonna be open.
Very good. So Avery went to 2, and she said, okay, let's look at that situation. And she's like, okay, I've got x equals 2. So I go looking along this vertical line for a dot, and you don't find one. If there's not a dot, it's not defined. You say f of 2 is undefined. That was a good question, Grace. Well done. Anybody else? Nicely done, Avery. In fact, hey, look at me. Look at me. What I actually was hoping somebody would say, and maybe somebody was thinking this, is that to answer number 4, because I've already answered 2 and 3, I don't have to look at any dots. I just look at those 2. That's it. Just remember, whenever you're doing an overall limit, you have to check left and right. You have to. Please hold.
And if like 2 and 3 were different answers, then 4 would be non-existent.
Perfect, 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 perfect. If 2 and 3 are different answers, 4 is non-existent. Pretty good. Okay, it should only take you like, I'm serious, like 3 minutes. Do the rest of the page. Go. I'll just walk, and if you have a question or something that pops to mind, just stop me. And then we'll kind of read the answers to you, because these don't have the answers written down. You don't have to finish labeling. That was just to kind of give you a sense of how to read this. From a common sense perspective, not much difference. Mathematically, when you're finding a limit, they'll always use the word non-existent. When you're finding the value of a function, they'll always use the word non-existent. I described the white green stuff. That's exactly what you want to do. Just go study the video, and that will make a huge difference. And after studying the video, just pretend it's questions. And once you've done that, I want you back to discuss the video. I get it. It's really hard when you miss it. It's not as good. That's what I do.
We did it. No, sadly, I think it's probably something to do, but if it doesn't work, it doesn't work. Well, I think some of our placing the pitch too close because I had trouble with technique when it was super close. I think we had the trash can too close, so we had to set back a little bit and like lift it. So yeah, so the attention tax people when they open the door. It'll be that.
Part of you kind of just slip your mind is that when you're finding a limit, they give you an extra. And they're just saying, what's happening in look up, please. Okay, no big deal, but one mistake a lot of people are making is that they're still so used to reading graphs where all the dots connect that it's kind of messing with your brain that they don't have to. So for example, like right here, look at number 5. 5 says the limit as x approaches 3 from the negative side. Okay, when I go looking for the appropriate spot on the graph, I don't look at the graph yet. I go figure out where x is just a little bit less than 3. Now watch my pen. Okay, anywhere along this line, as best I can draw it, it's a little hard to draw here, but anywhere along this line, that's where the x value is just barely less than 3. So straight. How did you? That's pretty good. Pretty good. Sit down and just admire that for a minute. I've always had this vision of this like assembly where and it would only like the only ones who would get it would be my calculus students, but I think it'd be kind of fun, you know. Like they open the curtain, there's nobody there, and I just get a whiteboard, I just kind of push it onto the stage and like have sound like so it creaks and stuff when you push it. And then I just kind of walk out and I just draw a really straight line. And like all of you cheer loudly. Kind of funny, you know. All right, look out. Look out. Hey, look out. Hey. So notice, hey, a lot of you, what you're doing is like, you go, well, do I look at this dot? I don't look at any of those things. I say, is there a dot that lands where x is equal to slightly less than 3? And there is. It's right here. They didn't draw it as a dot, but that's what I see, because I see the graph as dots. So I'm looking right here. And limit means, if that's the x coordinate that's on the function, what's the y coordinate getting close to? Just say it. 2. So this would be 2. Just out of the way. Maggie, does that help?
Yes.
All right. Questions? We got to speed up just a little bit. We're almost there. We got to speed up just a little bit. Apologize for that. Okay, I just want you to say the answers, and I'll listen. If you say them together as a class, I can usually hear if there's any sort of disputations among you. Okay, 5. What do you got? Say it.
3.
6.
3.
7.
3.
8.
9.
Nicely done. 9.
3.
Any questions? Perfect. We just got to get to the other side, and then we're done for the day. You're doing really well. Number 1.
3.
2.
0.
3.
3.
4. Non-existent. Good enough. Okay. Non-existent works. I sometimes abbreviate because I'm lazy. Does not exist. Okay. I'm efficient. 5. Where is it? That one. Sorry. 6.
2.
7.
2.
Work. 8.
0.
Nicely done. And 9.
1.
Perfect. Perfect. Okay, look it over. Look it over. Yes. You go heated calculus. Hey, I guarantee it. I cannot. I'm not going to say it's going to be easy, but the key to calculus is making sense of it. Like I've never had a single student, no matter how much they hated math, no matter how much they hated math when they came to this class, if they make sense of the idea, they feel amazing. Like I had a girl come back, I had her like 8 years ago. She's already gone through BYU, she's gone through graduate school, she's going on to get a PhD or something. She had to take some tests and she came back to just talk to me and say hi. And she literally said, tell your students, look, calculus will help you. She didn't major in math or anything even close to it, okay? But just the process of learning what it means to understand something has helped her immensely. So no, keep going. Okay, we've got to hurry. Sorry, I get too excited. 1 second. Pull up this file. Oh yeah, you feel it.
Yeah, I love it.
To me, if I don't understand math, it's torture. You have to understand it. Otherwise, it's just drudgery. Okay, this goes really fast. Watch me. Watch me. This goes really fast. Before we hit this, I gotta just explain my expectation for homework, because it's the first assignment I'm giving. Okay, I hope you've noticed I do things a bit different than other teachers sometimes. It's because my whole focus is on making sense of the ideas, right? Okay, so when you come back to class on Wednesday, Monday's a holiday, I'm gonna walk up to each person, and I'm just gonna ask a simple question. I'm gonna say, are you prepared to discuss the homework? Okay, what I mean by prepared to discuss is, you have tried every problem. Like you've read it, you've thought about it, if you kind of logically tried to come up with the answer, and then if you checked and it was wrong, and you just, don't spend a lot of time if it's wrong. Just kind of think about it, can't think of why, go on to the next one. Sometimes you do 10 of them, you're like, oh, that's the mistake I'm making. You go back and fix it, okay? Then all I ask is you are prepared to discuss. I mean, you have tried honestly each one. Okay, they're not in order of difficulty. I don't have the time to do that, okay? They're just whatever. So the last one could be easier than the first one. So you try all of them, you check each answer, you just take note of where you're having questions. Then you are ready for a very productive discussion on Wednesday. That's what you need to do, okay? Good. Here we go. Okay, we're back to a formula instead of a graph. This is a piecewise formula. It's really easy to understand. Normally we have one formula that you use to find every y coordinate. Plug in an x, get a y. With piecewise, the only difference, we now have 3 formulas. Here we have 2. The first column is the formulas for calculating the y coordinates. The second column is like the index, or kind of table of contents or whatever. It tells you which x's get used with this formula. So in this case, I'm not allowed to actually plug in an x that's 0 or less, according to this formula. So this graph would not have anything when x is less than 0. But when x is between 0 and 3, I use this formula. If x is exactly 3, I use this formula. If x is more than 3, I use this formula. Okay, please don't forget step 1. When you're solving a limit, always factor and divide if you can. None of these require that, but I have seen on the AP test, and we'll hit some in the future, where you do have to factor within the piecewise. Okay. Every with it. Let's go to here. It says find the limit of this function, which means find the y coordinate when the x coordinate is just a little more than 3. Well, we don't read a graph this time, we use the formulas. So we say, well, when x is a little more than 3, which formula, that's the first question whenever it's piecewise. So I want everyone to raise their hand on this. Actually, we'll do secret ballot. You're just going to do this. 1, 2, or 3. Which formula should I use? 1, 2, or 3 when I'm answering this question? Show me your fingers. Show me your fingers. The split. I'm looking for when x is a little more than 3. Look up here. This says when x is less than 3, greater than 0. That doesn't apply. This says when x is exactly 3. That doesn't apply either. It's this one. Question. So you can do it mentally, you can write it if you want. I just kind of write it over here and say, well, let's see, 2 multiplied by 3 plus, add 1. Well, that's going to be really close to what number? 7? 7, so the limit's 7. Remember, finding a limit just means find the y coordinate. It's all about recognizing which y coordinate. It's also about recognizing how to kind of simplify when necessary. Nicely done. Avery says, hey, it's 3 minus, so that means it's less than 3, so I have to use this formula. So thinking here, let's see, we've got 3. So little less than 3 squared minus 2. Well, close to 7 again. Okay, trick question. Come on. Focus. We've got 2 more minutes. Focus. Answer number 3. Just raise your hand, please. Where should you be looking? Come on, hands, please. Answer number 3. Where should you be looking? Just raise your hand if you know. Where should you be looking to answer number 3? Some people got fooled again. Whenever you do an overall limit, what do you always look at? See how easy they fool you? You look at left and right limits. So what's the answer to 3? 7. To answer this one, you have to look back up here again. That one's 2. Question? Okay, let's keep going. We're going to just wrap this up and then the day will be over. So you get these answers. You have a little bit of something for your notes. So I want you to go here, just raise your hand when you have it. Raise your hand when you have the answer. What would be the limit when we're approaching, let's see, 1 plus? I got it. Raise your hand when you have it. Come on. I want to get your answers down so you can take this home as notes. What is it? Sam? Sam's 4? Yeah. Sam says 4. How many vote with Sam? 4 is correct. Do 6. Come on, do it. Do 6. Do 6. Come on. Stay with it. Do 6. A little bit less than 1. A little bit less than 1. Let's go Colton. Colton says 1. How many agree? Hands. Come on. Colton. Good work. Number 7. What? Just look at it. What is it? Sim. Non-existent. G of 1. This says whenever x is equal to or less than 1. So now x is exactly 1. 2 times 1 is 2 minus 1 is. There's those answers if you want to do your notes. You kind of check yourself.
The 7th, whatever that is. I think I would try to see if I can actually stay home so I can actually read it. I don't have a physical copy yet, so I'm reading on my phone.
Just sneak by the hallway. There's kind of narrow there. I just went around a lot of everything. Take the right away. So what I'm looking for is, so when I answer the question, it's really the same thing as this one. It's the dots that so I don't pay any attention to that. Oh yeah. So like that's 1, 2, 3, 4. So that was 4.
Yeah, so because I tried doing it and so got it. Number 2, so x is a little bit more than 0.
So limit's different. When I'm trying to figure out whether the limit as x approaches 1 exists or doesn't exist, I have to look at the value of the right-hand limit. I the left-hand limit.
It's not like you have to look at the
That's how that comes.
but you look at where
So
the
there's a
line
different thought
is.
process.
Is that what you mean? Yeah, can you define it? Really?
So I was gone last week and I keep looking and she said we can try. Like I got her notes. So it's
X is
So you're good. There's nothing to turn in. The quizzes, we just, drop about a third of the quizzes. So in your case, since you missed 2 in a row, you'll probably want to come back later in the term and look at all your quizzes and say, hey, can I drop these instead of these?
Oh, you can drop the
A third of the quizzes will drop. That allows for some absences and bad days or whatever. Does that make sense? It just gets really hard to make them up. So we'll just drop about a third.
Okay.
You're welcome.
So I'll just have to be like, hey, I was gone this day.
Right.
Drop them.
Yeah, we're just going to look at all your scores and say, oh, let's adjust the scoring. Instead of dropping this one, which was a really good score, we'll drop this one, which was 0.
Yeah.
Something like that.
Awesome.
But you'll have to remind me, I'll forget.
I will.
The other thing you want to do for sure is you want to study the videos that you missed. So go to the website.
They're just on the website.
Yeah, it's way important that you really watch those and do it just like you're in class. Watch the video, take notes, write down any questions that just come to mind, and then you discuss it with me or somebody else. Perfect.
Perfect. Thank you so much.
Good job, Maria. Sorry about the name there.
No, you're good.